Using the epsilon n definition of the limit, show that the limit as n tends to infinity of 3n plus 2 over 2n minus 1 is 1.5, which is really just a fancy way of saying 3 halves. And you can sort of see, if you factor out the n's and cancel things out, you'll see that the limit here should be 3 halves. So they've got the right limit, obviously, but can we use the epsilon n definition to actually show this? Okay, so what do we need to do? Well, we need to show that for any choice of epsilon, we can find a capital N, sometimes called capital N epsilon, to remind people that the choice of n often depends on which epsilon you've got. Stricter, smaller epsilons will require larger capital N's. Okay, but we'll just leave it as is. Okay, so we can find a capital N so that n being greater than this capital N implies that our function, not our function, our sequence, okay, as a function of n, is close enough. So 3n plus 2 over 2n minus 1. Okay, and I'll write the 3 halves rather than point out the 1.5. Work with the 1.5, and then my first step is going to be write it as 3 halves. Okay, so that this difference in absolute value is less than whatever choice of epsilon. Okay, so we need to show that this is true no matter what epsilon we pick. A good way to approach this, we've got to find the n. That's all the proof is find the n and show it works. Okay, that's all an epsilon n proof is. So sometimes a good approach is to work backwards from what we want. Okay, we want epsilon to be greater than this. Okay. What could we do? Well, we could maybe write this so that we've got sort of a common denominator. Right? That might help. Okay. So we could get a common denominator of 2n minus 1. Okay. How are we going to do that? We can't just do 3n minus 1 and 2n minus 1, but we could say 3 halves times 2n minus 1 all over 2n minus 1. There are other ways to do it, multiply everything over. Actually, you know what, that might be simpler. I want to reduce the fractions that I've got. So we're going to multiply top and bottom here by 2, and multiply top and bottom here by 2n minus 1. Okay, that'll avoid fractions, but we could have done it the other way. Okay, so we'll get 6n plus 4 all over 4n minus 2 minus 6n minus 3 all over 4n minus 2. Okay, the 6n's will cancel out. 4 minus negative 3, that's going to be 7. Over 4n minus 2. Okay. We can write that as 7 over absolute value of 4n minus 2. So that needs to be less than epsilon. If we can get a statement like this, we can transform the 7 over absolute value of 4n minus 2 back to what we need. Okay, so let's play around with something like that. Oh, mind you, it's still just rough work. We could cross multiply. You're not going to change the inequality because everything here is positive. The epsilon is positive. 4n minus 2 in absolute value is positive. Okay, so we get something that looks a little like that. Now, for values of n that are greater than or equal to 1, 4n is greater than or equal to 4. So 4n minus 2 is greater than or equal to 2, so it's going to be positive. So 4n minus 2 is its own absolute value after a certain point. Okay, so what we really need to do is show something like this. Okay, as long as our n's are greater than or equal to 1. Okay, and then what can we do? We could say 4n has to be greater than 7 over epsilon plus 2. Then divide everything by 4. So we could say 7 over 4 epsilon plus 2 over 4 is 1/2. Okay. Or we could combine things. Let's say 2 epsilon over 4 epsilon. So 7 plus 2 epsilon all over 4 epsilon. That's fine as well. Or you could say 7 over 4 epsilon plus 1/2. Either way works. But this would make a great n because we've got little n past this value. Okay? So, there we go. Now, what do we do? Well, we've got to write the actual proper proof, and the proof always has to start with the same sort of statement. Pick some epsilon. Okay? Let epsilon be some choice. Okay? I usually say, let epsilon be arbitrary. We don't care what epsilon is. This will work regardless of what any antagonist chooses epsilon to be. Okay, we claim n equals, what do we want here? We'll write it as the 7 plus 2 epsilon over 4 epsilon, because why not? Okay, we claim that this will do. Okay. And now, the only thing we're allowed to do at the start of our proof, we must suppose that n is greater than this chosen capital N. That's it. Just from this assumption, we need to work down to the absolute value is less than epsilon statement. Okay, so what can we do? Well, I suppose it doesn't hurt to rewrite this. Okay, like that. Okay. Now, since we're working with a sequence, actually, we don't need to. I was going to say we could assume the n's are integers. We're not even going to need that. I was just going to say, well, because this expression here, it must be at least 1/2, and since n's got to be an integer, n will be at least equal to 1, but we don't even need that, as you'll see in a moment. I thought I needed something, I threw it out. I don't have these, there isn't a fast way of this is guaranteed to work. You've got to play around with it every time you do these sorts of proofs. You can notice patterns, but... Okay, so here, let's say, since epsilon is positive, 7 over 4 epsilon is positive. So n, which is greater than our capital N, which is greater than 1/2. Then 4n is greater than 2, and 4n minus 2 is greater than 0. So 4n minus 2 is its own absolute value. We're going to need that in a moment. Okay. Okay. Notice that n being greater than 7 over 4 epsilon plus 1/2 can be rewritten as n minus 1/2 greater than 7 over 4 epsilon, and then multiply everything by 4. Okay. But as we just noted, absolute value of 4n minus 2 is just 4n minus 2. So what we really have is the absolute value of 4n minus 2 is past 7 over epsilon. And we can rearrange this to be epsilon is greater than 7 over absolute value of 4n minus 2. Okay? And now we're home free. We just need to unpack this. Okay, put everything in absolute values. And then, what was it? Break the 7 up into, it was 6n. The 6n's canceled, and then we can write 7 as 4 minus negative 3. Now split things up. The 6n and the plus 4 go to 1. And then minus 6n plus 3 goes to the other. Okay, and that can simplify to 3n plus 2 over 2n minus 1. And the other one can simplify to... Oh, that should be a negative 3, not a plus 3. The other one can simplify to 3 halves. As desired, we'll just reiterate. If our n is past this cutoff capital N, then the terms in our sequence get as close as anyone could ever want. You pick an epsilon, I've got you covered. Okay, and that completes our epsilon n proof.